file system, but the other subsystems also, like say process, similarly the memory subsystem and so on. So we have simplified this algo-lget algorithm so as to understand what exactly is happening. If you are reading the book, the description is quite confusing because there are terms which actually what refers to two entities that is same data structures are there in memory and similarly on disk also. Okay, same data structures they are there on the secondary media, that is your hard disk, and similarly there is the memory. When the kernel is actually working with your system, right, you will find that it always refers to data structures which are there in the memory, because reading the data structures from this takes a lot of time in terms of milliseconds, right? So it always refers to memory, and those data structures are updated at regular intervals. They are updated at regular intervals on disk at after regular times. So what is that system call which makes use of or which is responsible for updating the data structures from memory to the disk? Yes, anybody in the class? Which system call is responsible for updating the kernel data structures from memory to the disk? Anybody remembers? I have told you many times. I just want to know whether you pay attention or not. Yes, from A division, what is that system call which is used for updating the kernel data structures from memory to the disk? Nobody from A division? Anybody from B division? So I find people have become very habituated of just going to Google and not remembering anything. That is actually not going to help you. It is something like this. If at all, to the third year CSC students, if I ask you to write, let us say, a quick program, right? How many of you can write immediately within 2 minutes? What I'm saying? How many of you in the class, a strength of near about 160 students, can write the quick sort program immediately? Anybody in both the divisions? Nobody in the class? Reason being that you people have just become what habituated of copying the what code from the net. So nobody in both the divisions, which so I have told you many times that you have this F sync, right? So this system call updates your data structures regularly, and this is very critical for working of your file system and similarly working for your databases and so on. Okay, so this happens to be the very important system call. So let's come back. So what is actually being done here? We are referring to an algorithm called as the I-get. Okay, and then you have another algorithm called as the IMR. Where from this I-get is coming? I told you last time that is you have this when you do open, okay, open some file. Let us say I do open my file. So when I open my file, you find that it actually goes to the AMI function. So what it does, it converts the name to the inode, whatever the inode of that particular file is. And when it is converting to that particular inode, and you are opening this file, So this file basically has to be brought in the memory. This file has to be brought in the memory, and similarly this inode is also to be brought in the memory. Okay. So what is happening here is that we have a data structure called as the inode cache, or you can call it as the inode table also. You can call it as the inode table. So what is given for us is the input is the inode number. Okay, and inode number we are getting through the NEMA system call. We are getting inode number through the NEMA system call. So having given the inode number, what is done? We basically want the inode to be brought in this particular table called as the inode table. So we want inode to be brought in the inode. So there are different cases, that is how the inode basically is actually say brought in the inode table, and how the inode is actually locked. So if you see the flow, so in case of we find that there are what say two alternative ways. So one is basically this particular if statement. Okay. So what it does, so you have this one, and what it checks if the inode is in there in the inode cache or the inode table. So what are we doing? We have the input, that is inode number. So it means that this particular file is existing. So this file is existing on the disk. Therefore, you find its inode should also be there on the disk. Its inode should be there on the disk. So that is basically the permanent location. That is the permanent location of the inode, and that is on the disk. Now, when you are going to work with the inode, so the inode should be brought in the inode table. So what can happen is that this particular inode and this file might have been used earlier. This inode and the file might have been used earlier, and therefore you find that this particular inode may be existing in the inode table. May be existing in the inode table. So this is what this if construct is telling us, that we check for inode in the inode table. If it is there, okay, filled up with all the data structures, then we follow this path. So what is happening here? We come to this one, and then we check for another thing. And what we are doing here, we find out whether the inode is locked or not. Okay, so inode is locked when some process or the kernel is actually making use of that particular inode. Inode will be locked when a process or the kernel subsystem makes use of the inode. So if that is the case, you find that this particular inode will be locked. Okay. And when we find the inode is locked, then what we should do? We find that we miss the kernel actually slips here. Okay. So when it slips, you know that you have actually come up to this particular point. And when this code wakes up, okay, that is what we are writing here. So when this code wakes up, you actually start from this particular point, and then you start what? Doing rest of the things. You start doing rest of the things. And then this is the notation that is being followed in the code. What it says, that is this particular say code, right? It actually what wakes up on the event when the inode is unlocked. On the event when the inode is unlocked. So there are so many parallel paths. You find that this particular say thing maybe might have been called by some process, and therefore we find that that process might have got open. It calls name I, and in the name I you find that you actually require the inode. So you come up to this point, and then you find that this particular say path actually sleeps here, and when the inode is say unlocked, then you call through this and then you go for checking this next condition. So now what is happening here? You find that inode is there in the inode table. This is what you have checked. Similarly, you find that now inode basically is unlocked, right? Now this inode is unlocked. This is actually not being used. Then what we should do? We go for checking the inode in the unused list. So what this means is it is something like this. And this is a pattern that is used throughout the book that you should always know. So let's assume that there is a list and we call this thing as the unused list. Okay, unused list means what? Different inodes, those inodes which were actually used earlier, so their numbers are basically written in this. So if you find that the inode that you are referring to, because the inode number is given, so if you find somewhere here the inode number, let us say 300, and if it is there in the inode say unused list, what you have to do? You have to remove it from this unused list, right? Now you will say what is the use of this particular unused list. So it is something like this. What the kernel does is that when you are working with the inode is over, now you know that the inode is there in the inode table. So this is the inode that you are working with. But now the kernel is not working with the inode. Inode is there in the inode table. So what the kernel does, it actually doesn't remove the inode from the inode table. It does not remove the inode from the inode table. It keeps the inode here itself, and what it does, it just writes its number here. That is 300 is the inode which was being used, but now it is actually not being used. So that is the reason that we are actually making use of this particular unused list. Is it? So after having satisfied these two conditions, inode is there in the inode table. Now it is not locked. Then you find that it is there in the unused list. So you remove it. Now you can actually work with the inode, and that is what we are showing it here. You remove it from the list. That is what we have shown right here. Then you have this field called as the reference count in the inode. You have this reference field called as the reference count. So this is incremented by 1. And the meaning is like this: when you are opening a file, right? So automatically it increments the reference count, right? So if there are say, if there are, I mean, if there is an entry called as 4 in the reference count, so it means it has been opened 4 times. It has been, so this is what we have done. Then we so that make use of this particular item. So what so what is ultimate? So let's say what is the input? You find that the file is existing, and as the file is existing, you find its inode right? And similarly, you find that its copy existing in the inode cache, the inode table. To make use of this file at inode, you have to check if this particular say inode is there in the inode table. So we are following this path for the time, and then we find that the inode is there in the inode table. Then you find whether it is blocked. So if it is blocked, you have to wait till it doesn't what wake up. Sorry, 18 liter it doesn't actually get unlocked. When it gets unlocked, you are coming here. You check for if its number is there in the unused list. Okay, so if it is there, then what you can actually make use of this inode by removing it from this increment the reference count bit, check its log bit, and then you return from this algorithm that is that. So this is one path. Other path is that let us say that this particular file and similarly inode is actually being opened for the first time. This particular file is being opened for the first time since you have actually started your operating system. Since you have started your operating system. So if that is the case, so this path basically will not be followed, and then what you find you are coming directly here. So as the inode is not there in the inode table, what you have to do? You have to bring the inode from where you have to bring the inode from the disk. So I will show it here. Next time onwards, you should assume that always there is a permanent storage of different data sources on disk. So from this, you are going to bring this particular inode and store in the inode table. That is what we are actually doing here. So we show it here. Read inode from disk. Now this simple statement basically is actually being implemented by an algorithm called as the block read. Okay, so you are going to read the data from the disk. So all the work is actually being done by the lower level algorithm called as the block, and we do not go more into detail. We just assume that it actually reads the corresponding block. We assume that it actually reads the corresponding block so as to at least understand these data structures. So what it has done, it has read the inode from the disk, and then what you have to do, now when I say it has read the inode from disk, so this will be put somewhere in the memory. This will be put somewhere in the memory, right? So let's assume that this is the inode structure, right? Where you find that you have read the inode data from the disk. Okay, so you can say something like it is an object. So it has read this particular inode and it has put this thing in the memory. So it is there in the memory. Then what you can do, as it is done here, you increment the reference count. Okay. Then similarly, when you are returning, you set the log bit, and then you can actually return the inode. You have this statement that is put the inode in the inode phase. Means what? This particular inode that you have read it in the memory, so it may be basically located somewhere in the memory, right? So we want to put this in the inode table. So how it is done? You know that there are two pointers. So those two pointers basically point to the what the other inodes. So what you are doing here, that I mentioned here also. So if this is the inode structure, so there are two pointers. So I set this pointer to some inode here, and similarly I set this pointer to some other inode that is actually existing here. So I am linking this particular inode structure with the rest of the inodes, and it actually becomes part of the inode table. It becomes part of the inode table. Okay. So what we are doing here, our aim basically is to, we are going to open a file, right? We are going to open a file. So when we say we open a file, there are two entities. One is the data, and other is the metadata, that is the inode. So inode basically has to be brought there in the inode table if it is not already there. Okay, so if it is not there, then this path is not followed. You follow this path. You read the inode from this. Okay, initialize these two pointers. It becomes part of inode cache or inode table. Okay, and then you are returning a pointer to the inode. This is one thing. The other thing is that this particular file might have been opened earlier, and because it was opened earlier or used, you find inode is already existing in the inode table. So if it is that, then you check if it is not being used now. If it is not being used now, so how we can find out if its entry is not there in this unused list? Then we find that this particular inode is actually not being used. Okay, sorry, if its number is there in this list, then we find that this inode is actually not being used. And then what we do? Remove the number from this, and then we give, I mean, what? We the unused list, and other is the annual table. That, sorry, yes, the other one is the annual table that we are actually making use of. So things are fine for this algorithm. Now you'll find that when we move to the next algorithms, then you find things are what? Say slightly confusing. So be careful in writing these algorithms. And then I find that every year there are many students who just what? Write the things in just opposite way. So you know that this idea algorithm is for inode actually existing, or for an inode which is not existing. Whereas its other counterpart, which we have mentioned, what is that? Analog. So analog is for creating a new analog. Analog is for creating a analog. So this is done when you are going to create a new file, right? So when you create a new file, it requires a new inode, and that new inode is created by this algorithm called inode, right? So things are simple. Only thing is that it is actually not mentioned properly. It actually mentions about the hash table and so on. It's talking about hash table in the book. What we have done, we are not mentioning hash table. The reason is that for this set of data structures and for other data